We now cover another way of representing a vector. In this case, we're going to take advantage of our unit vectors and our knowledge about multiplication of a vector by a scalar to rewrite a vector not in polar form but what is known as in Cartesian or rectangular form. A vector, any vector, can be broken into distances along the unit vectors. In our case, we'll restrict ourselves to Cartesian vectors for the minute. And so if you have a vector, say A, it's possible to write that by some scalar amount, let's call that a sub x, times a unit vector that points along the x, and then add to that an amount along the y, and then add an amount along the z. This amount right here called x sub x is called the x component. Of the vector A. It may be a positive or a negative number. If you want to think about it in just 2 dimensions, it's the x-coordinate back in graphics. If you think about the point in space that represents the tip or the end of the arrow and the beginning of the arrow starting at the origin. This person right here is the y-coordinate. Y component of the vector A. And likewise, this will be the z component. At least a lot of the stuff in this course will be restricted to 2 dimensions, but obviously if you were working in engineering or advanced physics in college, you'll have to work in 3 dimensions. We don't build 2-dimension buildings. It'd be really hard to put people inside them. Alright, so let's take an example of how we can do this. This one says, let's draw the vector B written as this, 3 times I hat minus 4j hat. So the first thing is let's draw it. So let me draw a coordinate axis. There's my y-axis and there's my x-axis. And I'll draw myself a vector. And I need to go 3 units along x, and I need to drop down 4 units along y. So this is minus 4. And this is plus 3. This is some angle theta. And this is the magnitude b. And from trigonometry, I happen to know that that magnitude would in fact be 5. But this arrow represents the vector b. So we see that this tells you how far to walk along the x direction. In this case, it says walk 3 units in the positive x direction. I know it's positive because it says to go positive. This, j, says along y, walk 4 units in the negative direction. So we got to walk down 4. Now my scale may not be right. This side should in fact be a little bit bigger than that side. But that's the idea of drawing a vector in Cartesian. Notice it's vector addition. You're walking along one way. That's the first vector right here. And then you add to that this next vector, which says add minus 4j. So it's the addition of 2 vectors. The only purpose of the unit vectors are to tell you direction, and the components tell you how far along those unit vectors. Now I'd ask some other questions you could be asked. You could be asked, what is the x component? That's easy. It's the number right in front of I hat. So that's the answer, 3. And ask you, what is the y component? That's easy to read too. It's minus 4. It's the value just in front of j hat. Why will we like this form versus the polar form? Well, the advantage is that the Cartesian form is the easiest for doing mathematical calculations, for adding and subtracting vectors. Well, the polar form is usually what a person wants at the end of the problem. How far is the beam? How fast was your car going? I was going 50 miles per hour. They don't ask you, oh, it's going 30 miles per hour east and 40 miles per hour north. They want to know the hypotenuse. So you see, we're going to be converting between a polar form where we know the hypotenuse is an angle and we need to find the sides using our trig, or we're going to have these sides in trig and we're going to need to find the hypotenuse and angle. So this is why trigonometry, the sine and the cosine, the tangent, and the Pythagorean theorem play such an important part, because they provide the way to go from the polar representation to the Cartesian and back. So that's why we need trigonometry. All right, let's talk about adding vectors. I said adding vectors was easier in Cartesian form. Why? Because when you add two vectors, you simply add all the x components together to find the total x, and you add all the y components together to find the total y vectors component. Okay? So if we're looking at a plus b equal a new vector c, if we know the x component and y components of a and the x component and y component of b, we simply add both of the x components, x component of a and x component of b, and that gives us the x component of c. And we add the y component of a and the y component of b, we get the y component of c. Now, this mathematics may look somewhat maybe confusing, all right? But you've been doing it all your life. When you walk to the store, when you drive with your parents to the store, you've been doing it even if you didn't know it. So let me show you how that works out. I've got a system here, and let's say I want to add a couple of vectors. I'm going to start with a, and let's say a goes like that. So that's a. And I plan to add, of course, the vector b. Maybe vector b goes like this. And then we know that the total of those starts from here and goes out there. All right. So this is a plus b is c. We know that. And let me document that's a. And let's document that this is b. And now I want to go and do some things. I note that that right there is a sub y, the y part, and this is a sub x. So this is the x component, the y component, and the total vector. Now let me go one step further. This quantity right here, that's b sub x. And this quantity right here, from here to here, that's b sub y. Now, let's look at the purple vector now. The purple vector goes from here to here. That's its y component. That's how far you'd have to walk along the y-axis to get to that point. And you'd have to walk this far to get the x part. So what do we see? Well, we see what the formula I just wrote. That if you want to get along the purple from here to there, then you'd have to walk a sub x, and then walk an additional distance, which happens to be b sub x, that is the x side of the triangle, of the red arrow, and that would give you the total distance you walked along the x, which we call c sub x. The side, the purple side right here, whose hypotenuse is this. And along the y, you had to walk up a distance a sub y, and then you had to walk up the distance b sub y to get to the tip. The total distance along the y is this side of the triangle right here for my purple hypotenuse, which we call c sub y. So the x part of c is the x part of a plus the x part of b. The y part of the c arrow is the y part of a and the y part of b. So what happens in the x does not affect what happens in the y. What happens to the y does not happen what happens to the x. These are what are known as orthogonal coordinates. Now we often say that's because they're at right angle, but orthogonal really means, if you would, that they're independent of each other. So when I'm driving to Walmart from here, and I go, say, 1 mile east and 2 miles north, all right, 1 mile east and 2 miles north, and if then I took another road, and that road went 2 miles east, and I now arrive at Walmart, what I've done is I've gone 3 miles to the east. The fact that you're going east does not talk to north. And I've gone 2 miles north. What happens along north and south does not talk to what happens in east and west. So when I'm going on a north-south street, I'm not going east and west. I'm only going north and south. This is type of rectangular grid is how we build things. Now, we could, of course, go diagonally, but then I could just as easily have gone along east-west road and then a north-south road and got to the same point. So what happens along east-west does not talk to what happens along north-south. And that's what that fancy formula basically was saying. So if you break this thing into x and y components, if you know these guys, you can simply add up all the east-wests to get the total east-west. You can add up all the north-souths to get the total north-south. That's the way you add vectors in Cartesian form. Now, let me give you a problem. It says, okay, let's do this. A and B, here's what A is. Here's what B is. What's A plus B? Well, there's several ways you can write this. Some people like to do it like this. They actually like to build some sort of a grid. I don't, but many people do. And in the A, they write 3 meters. This is the I hat part. There's the J hat part. Minus 5 meters, 4 meters, and 2 meters. And then they say A plus B. And they say, well, you just add this column. 3 plus 4 is 7 meters. Minus 5 plus 2 is minus 3 meters. A plus B is 7 meters I hat minus 3 meters J hat. You also could have done the problem like this. You simply could have written them 3 meters I hat minus 5 meters J hat plus 4 meters I hat plus 2 meters J hat, and then simply added them up. A plus B is equal 3 meters plus 4 meters, all of them with I hat, plus minus 5 meters plus 2 meters J hat. A plus B is 7 meters I hat minus 3 meters J hat. It is easy to add vectors in Cartesian form. So if you're given a vector in Cartesian form, it's easy to add it.